All right, now we have a process, and we'll be able to do more complicated problems using our process. Here we're going to look at wave speed in the ocean using dimensional analysis. So if you think about water and waves, what do we need to describe that? Well, the density of the water is probably a factor, acceleration of gravity, and the wavelength of the waves. Don't know anything else that we could use, but let's see what we get with this. So here's our velocity. And once again, we're using this formalism that we're going to take each parameter that we think is relevant, raise it to a power, and then we're going to evaluate those powers. So we have density rho, which has units of mass per cubic length, acceleration of gravity, length over time squared, wavelength is length. So on the left we have velocity, length over time, and then we have these three terms, this to the A, the mass divided by volume, length over time squared, that's the acceleration, to the B, wavelength to the C, and we get three equations. Now we have three unknowns, so we can manipulate those. First thing we see is that the density has no corresponding unit on the left side. So A is 0, we get B and C, and so we get this. The velocity is proportional, so we don't have a numerical constant yet, but we have proportionality to the square root of g and lambda. Turns out that indeed is the case. Okay. So let's review this again, how we got A equals 0. Density depends on mass and volume. So if we look on the left side, velocity, here it is, there's no mass term there. So m to the A has to be 1. So A is 0. That's how we got that. Just want to make that clear. Now, we could do something a little more sophisticated and say, what if we introduce surface tension as a parameter? We did not include that here. So there's always a possibility that you're going to have to reevaluate what you've done to add more physics. And so what happens if we introduce surface tension? And surface tension has the units, you can look this up, has the units of mass divided by time squared. So now we introduce a new parameter. Here's our old equation. Had three terms, A, B, and C, with exponents A, B, and C. Now we have A, B, C, and now we're going to have tension to the D. So here's the equation for the units. But we already know we're going to have ambiguity here because we now have four unknowns, A, B, C, and D, but we only have three types of dimensions, length, time, and mass. So we have an issue, three equations and four unknowns. But this leads to a very interesting result. We may not be able to include surface tension in our analysis because we're ambiguous with respect to solving for parameter D. However, we do notice something very interesting. The term sigma over lambda squared rho g is dimensionless. So we have, remember, if you put in these units for sigma and build this, you'll find it's unitless. And we already know that the square root of g lambda has the units of velocity. So we can actually create an expression for velocity that looks like this. The velocity is proportional to the square root of g lambda, we already had that result, and some function, f, of this unitless parameter. We don't know what that function is. However, we now know that two parameters, square root of lambda g and this piece here, those two dictate the velocity. So if we were going to go in the laboratory and measure things, presumably we can measure all this stuff to find a rule for how the velocity behaves. We could measure sigma, surface tension, the wavelength, density, and gravity, and group the data this way. And we have 2 parameters that describe everything rather than 4. Here are the 4 parameters. Now, what does that mean? It means that if we were going to, once again, go in the laboratory and measure things, let's say we would like to measure 10 values of each parameter. If we were measuring these independently, we would have 10 values of 4 different things. That turns to 10,000 measurements we would make to prove this relationship. But because we now have some insight about what's dimensionless, we can just measure a small number of things, namely this product and this ratio, and we only have to measure 100 things if we want to make 10 measurements of each thing. So something to keep in mind. Those of you interested in extending your knowledge of this can go look at a theorem called the Buckingham pi theorem, where pi is the Greek letter pi. You can learn more about how to build measurement systems that are much more efficient after you've done a dimensional analysis. All right, let's now change the topic. We'll go to electrodynamics and thermal physics. Key result of studying electrodynamics is how moving electrons radiate energy. So if we were considering a moving electron and its radiation properties, what would be the things we would include? Well, it's moving. We're going to have the velocity electron with these units, the charge, and it takes a little research, but you can find the charge has this relationship, this group of units. Here's the background of it, that the force between 2 charges is proportional. The product of the charges divided by the distance squared. That's a force. And that's equal to mass times acceleration. So the square of charge, Q times Q, is equal to mass times acceleration times this r squared. So I've just done a simple arithmetic here. And what are these units over here? It's mass times acceleration, length over time squared, times distance squared. So charge squared, looked at in this approach, is mass times the cube of distance divided over time squared. So what's charge? It's the square root of this. And there it is. Now power, how much power is emitted by our moving electron? Power has the units of mass times length squared over time cubed. You think about it, you can get that going. So the question is, what group, what configuration of these 3 parameters produces units of energy, which is power per unit time? And so here's power. And we have our typical equation. And here are here's what you might call the unit equation. Here's power, speed to the A, charge to the B over 2. Remember, this is a square root. And velocity to the C. And we get their typical 3 equations, one from mass, one from length, one from time, and you put them together and guess what? There's no solution. That is, if you take the first and last equations and compare them, you get that b equals minus 2. But if you redo the problem with the second and third equations, you get b equals 2. And so what has happened? So it turns out, here's a little insight for how you can use dimensional analysis to figure out if you're on the wrong track. The problem is radiation from an electron does not depend on velocity. It depends on acceleration. So we started with an improper assumption that velocity is going to get us power. And it doesn't. So to redo the calculation, this time we'll use, instead of velocity, we'll do acceleration. So once again, power, here's the physics equation, not knowing A, B, and C. Let's do it in units. Here's power, speed, charge, and acceleration. Now we get three equations, and we do get unique solutions. A equals -3, B equals 2, C equals 2. I'm sorry to say that I used C twice. I see that now. See that C? That's the exponent, and that C is the speed of light. So let's be careful about that as we go through the rest of the lectures, But if we're careful, we'll see that if we put these values into this power equation, we get that power from an accelerating electron is proportional to the square of the charge, the square of the acceleration, and the inverse cube of the speed of light. That's our proportionality. What we don't get from dimensional analysis is the actual relationship has a 2/3. So that symbol goes from proportional to equal. But if you were being pressed on an exam, for example, to understand this structure, I'd say your professor might give you damn near full credit if you came up with this in view of the fact that the actual answer has that 2/3. I've actually had a student who told me he was rescued by using dimensional analysis in an exam. He was struggling with a problem, and he did a little quick analysis, got the answer, then he knew what he was doing. It put everything in context for him. So we've learned something here about dimensional analysis, but we've learned something about physics too. The velocity of an electron does not get you to a solution that produces power. Okay, let's move on. Stefan Boltzmann constant. Some of you who've done thermal physics may be familiar with this this famous thing. Let's change that. Sorry, got a little do little detailed corrections as I go through. This is a pretty old lecture. I haven't seen it for a couple of years, probably more like 4 years. So here's Stefan Boltzmann constant, and by the way, that's two guys, so we'll hyphenate it. It's not that the guy was named Stefan Boltzmann. It's two people. We wanted to develop this concept because it's critical in understanding Planck's radiation law, where the energy emitted from a black body, the total energy over all wavelengths is equal to, the total energy is equal to Stefan Boltzmann constant times the temperature of the black body to the 4th power. Right? So that tells us what the units of this constant should be, and they turn out to be mass to the 1, T to the -3, K to the -4. That comes from knowing the units of energy. Now, this is our first encounter with quantum mechanics. So what we're thinking here is, let's introduce quantum mechanical things. Planck's constant, which has this energy over time. You'll notice this is energy, mass times velocity squared. 1/2 mv squared is energy. Planck's constant happens to be energy per unit time. The Boltzmann constant, which is different, that's a fundamental thing in thermal physics. And it has these units. And of course the speed of light. These are three critical components in any quantum mechanical problem. And we'll use capital K right here for the units of temperature. So we can't use T. We already committed that symbol for time. So we're trying to evaluate the Stefan Boltzmann constant using these three key parameters, physical constants. So typical thing, we're going to do that sigma equals, it has these units, and it equals some h to the a, k to the b, c to the c. Once again, Unfortunate that I did that, but let's just be careful and we can handle it. So here's what we get for the equation for the units. And we have 4 equations now, right? We get one from mass, one length, one time, one temperature. And from this, we get A equals -3, B equals 4, and C equals -2. So if we put those back in this original equation right here, we now know A, B, and C. It has these values, and we get this. And by golly, that's the right answer. The Stefan Boltzmann constant, which is so critical. Once again, I have to fix these. Sorry. The Stefan Boltzmann constant, a critical parameter in quantum physics and black body radiation and so forth. Comes out to be this. The real value has a multiplier of p to the 4th over 60. Sorry, that's pi. Gosh. Pi to the 4th over 60, which is means our calculation is correct to within a factor of 1.6. So, hooray for that. Whoops. I apologize for these little things I'm doing, but they must be done while I remember them. So, okay, that's the end of this little segment, and we're going to have another piece of this lecture will pop up shortly.